We are going to discuss an example from G.Proakis book. Let us see an example 5.1.2, which is moving average filter. The question is, determine the magnitude and phase of h of omega for the 3-point moving average system y of n equal to 1 by 3 into x of n plus 1 plus x of n plus x of n minus 1, and plot these two functions for 0 less omega lies between 0 and pi. Now coming to the solution, as we are given y of n equal to 1 by 3 into x of n plus 1 plus x of n plus x of n minus 1. From this we can write h of n equal to 1 by 3, 1 by 3, 1 by 3. The impulse response as given as h of n equal to 1 by 3, 1 by 3, 1 by 3. First we evaluate the Fourier transform of the impulse response h of n, and then we will calculate the magnitude and phase response of h of omega. We know the general equation of finding h of omega is given by h of omega equal to summation n equal to minus infinity to infinity h of n e power minus j omega n. H of omega equal to 1 by 3 into e power j omega plus 1 plus e power minus j omega, which is equals to 1 by 3 plus 1 plus 2 cos omega. In general, h of omega is a complex valued function of the frequency variable omega. Hence it can be expressed in polar form as h of omega equal to mod h of omega into e power j theta omega, where mod h of omega is the magnitude of h of omega. Therefore, the magnitude theta omega equal to the magnitude and phase of h of omega can be written as mod h of omega equal to 1 by 3 into 1 plus 2 cos omega, and theta omega equal to 0 when omega lies between 0 and 2 pi by 3, and pi when omega lies between 2 pi by 3 and pi. This is the MATLAB code which is need to be executed. This simulation graph illustrates the graphs of the magnitude and the phase of h of omega. You can see here that mod h of omega is an even function of frequency and theta omega is an odd function of frequency. It is apparent from the frequency response characteristic h of omega that this moving average filter smooths the input data as we would expect from the input-output equation. Let us discuss an example 5.1.4. A linear time invariant system is described by the following difference equation, which is y of n equal to a into y of n minus 1 plus b into x of n, where a lies between 0 and 1. The question is, determine the magnitude and the phase of the frequency response h of omega of the system, and choose the parameter b so that the maximum value of mod h of omega is unity, and sketch the mod h of omega and angle of h of omega for a equal to 0.9. And also determine the output of the system to the input signal x of n equal to 5 plus 12 sin pi by 2n minus 20 cos pi n plus pi by 4. The given impulse response of the system is h of n equal to b into a power n into u of n. Since mod a is less than 1, the system is B-bow stable and hence h of omega exists. Now coming to the a part, the frequency response is h of omega equal to summation of minus n equal to minus infinity to infinity h of n into e power minus j omega n, which is equal to b by 1 minus a into e power minus j omega, which is equal to 1 minus a e power minus j omega, which is equals to 1 minus a cos omega plus j into a sin omega. Then mod of 1 minus a into e power minus j omega equals to root over 1 minus a cos omega whole square plus a sin omega square, which is equals to root over 1 plus a square minus 2a cos omega. And 1 minus a into e power minus j omega equals to tan inverse of a sin omega by 1 minus a cos omega. Therefore, mod h of omega equals to mod b by root over 1 plus a square minus 2a cos omega. Then h of omega equal to theta omega, which is equal to b minus tan inverse of a sin omega by 1 minus a cos omega. Let's see the b part. Since the parameter a is positive, the denominator of mod h of omega will attain a minimum at omega equal to 0. Therefore, mod h of omega attains its maximum value at omega equal to 0. At this frequency, we have mod h of 0 equal to mod b by 1 minus a, which is equal to 1, which gives b equal to plus or minus 1 minus a. We choose b equal to 1 minus a, so we get mod h of omega equals to 1 minus a by root over 1 plus a square minus 2a cos omega. There, theta omega equals to minus tan inverse of a sin omega by 1 minus a cos omega. This is the code for MATLAB execution which is to be done to this problem. Let us see the frequency and phase response. The frequency response for mod h of omega and theta of omega is obtained using MATLAB, and we can observe that the system attenuates high frequency signals. Coming to the last part, the input signal consists of components at frequencies omega equal to 0, omega equal to pi by 2 and pi. For omega equal to 0, mod h of omega equal to 1 and theta of 0 equal to 0 for omega equal to pi by 2. Mod h of pi by 2 equals to 1 minus a by root over 1 plus a square, which is equals to 0.1 by root over 1.81, which is equals to 0.074. Theta of pi by 2 equal to minus tan inverse of a, which is minus 42 degrees. For omega equal to pi, mod h of pi, which is equals to 1 minus a by 1 plus a, equals to 0.1 by 1.9, which is 0.053. Therefore, the output of the system is y of n equal to phi into h of 0 plus 12 into h of pi by 2 into sin pi by 2 n plus theta pi by 2 minus 20 into h of pi into cos pi n plus pi by 4 plus theta pi, which is 5 plus 0.888 into sin pi by 2 n minus 42 degrees minus 1.06 cos pi n plus pi by 4, where n lies between minus infinity and infinity. Thank you.